everyone's there. It's just this laptop that's connected to the audio.
Actually, I need to check. Claire, can you hear us?
Yeah, we can hear you.
Okay, thank you. Okay, wanted to see whether you could hear if Luca or I spoke from that side. So thank you, everybody. It is a pleasure today to host you all at Siddharth Nayak's defense. So Sid and I started here in 2020. So the first time I met him was on Zoom. So it's nice that you actually end with a defense, which is you're in person, but half your committee is on Zoom. Again, it has been an incredible pleasure working with you, and I'm very excited to have you share with everybody else today all the work, the amazing work that you've done over the course of your PhD. And I'm guessing we're going to have a fair number of jokes here, right?
Yeah.
Rock-related jokes. So classic rock.
Yeah. Hello, everyone. Welcome to my PhD defense. Today, I'll be talking about my dissertation titled Stairway to Autonomy. As you can see here, there's a stairway. Before I start, just as I mentioned, I wanted to make a quick note that there are quite a few references to classic rock songs in this talk. So brownie points to anyone who is able to identify all of them. So yeah. So there have been a lot of robotic applications in recent years that require multiple robots to cooperatively solve tasks. A few examples include environmental monitoring, where multiple robots or drones survey an unknown region. You have search and rescue, where multiple drones deliver first aid to people trapped in unknown regions, where you have natural disasters. You have spacecraft operations where multiple satellites are working together to avoid collisions with each other. You have assembling products with robots in factories, and a few futuristic applications that might come up in the future include robotic household help with multiple robots and advanced air mobility where you have air taxis. So this motivates the creation of algorithms that can handle the control and planning of multiple robots in an autonomous fashion. So let's take a look at this futuristic example where you have multiple robots and you want them to help you out with some household chores. And let's say that you want to host a party, and you give this human instruction to these robots, and based on this language instruction, the first robot replies that it is going to go and decorate the room. The second robot replies that I will go and get the food items from the pantry, but it also requests for help. Now, based on this call for help, the third robot says that I'm going to help you with the food. Now, based on this discussion, you know that some of the chores are being handled by the robots, and now you can go and invite some of your friends. So this example showcases that robots in the future will need to interact with human beings and understand their intents and carry out tasks in a cooperative fashion. But achieving this involves a few technical challenges. The first one is long horizon planning. So if you look at the tasks required by each of these robots that are required to complete the task, the first agent has to navigate to the pantry n number of times, pick up the food item, navigate to the living room, and put the food item back on the table. And if you look at this, each of these subtasks requires multiple low-level actions. For example, the navigation action here requires the robot to move like 4 steps ahead and take a left along the hallway, and then again take a right, and so on. Similarly, like picking up something requires you to have good low-level control on the picking up action. So keeping track of such long tasks is hard in robotics because firstly, they might forget what they are supposed to carry out in a sequence, and secondly, that they might not be able to understand what all things are required in the future in an uncertain environment. So the next challenge that I want to point out here is partial observability. This just means that agents do not have a global view of the environment and do not have information about what all things exist before you even enter there. Now here, each of the robot, so once these two robots enter the kitchen, they have different views of like what they see. And they need to like make decisions based on this partially observable view of the environment. Now, the challenge here is that they need to have a general consensus about what actions are required and from these partial views and make a decision that cooperatively solves the task. The next challenge is exploration. So since most of these robots are working in partially observable environments, these robots or these agents need to explore this environment. And in this case, like since these two robots are trying to find food that they can deliver to the living room, they need to find out where's the bread and where's the cake. And which means that they need to like find out, like figure out where is it more likely to find bread and where is it more likely to find a cake. The next challenge is multi-agent control. So if you look at this, consider the scenario where while these robots are moving along in this kitchen, a glass falls from the countertop. Now, once this glass falls, these agents need to figure out which agent's fault was it. And figuring that out is hard in multi-agent setting, so this challenge basically translates to you assigning credit to the actions of agents that these different agents are executing in the environment. And since they are taking these actions simultaneously, it's hard to like figure out which agent did what. Another challenge that arises is in these situations is safely navigating in environments. Now, once this glass has fallen down, you want these robots to like navigate without crashing into the glass, which means that you need to navigate without collisions, which means that they need to create safe trajectories or like predict safe plans, and also like navigate around it. So let's take a look at a few different prior approaches that people have taken to like solve these problems. A few broad methods include using offline data and demonstrations, where you use data collected from experts collected from experts to train a model to predict actions based on the inputs. And these methods are quite prevalent in scenarios like self-driving, where you have abundance of data collected through drivers. The second broad set of methods include curiosity-driven exploration. So curiosity-driven exploration is basically agents being made to explore the environment based on its curiosity. You reward the agent to explore novel states that they have not encountered before. The third setting involves reward shaping, where you basically shape the reward based on what behavior you want to get out of these agents. This basically includes setting the rewards in a set in which for objectives that you care about. So for example, in this case, you have a term which involves you reaching the goal, but you also want to avoid collisions and maintain balance and so on. So you need to add all of these. Another popular set of approaches include hierarchical reinforcement learning, where you have a master policy and you have a bunch of sub-policies. The master policy chooses one of these sub-policies based on what you want. And each of these sub-policies is an expert on doing something. So for example, sub-policy 1 is an expert at navigating, sub-policy 2 is an expert at picking up things, and so on. But if you look at this, each of these methods have a few limitations. The first one is the assumption of availability of a lot of data to train these models, which you can see, which is required in offline demonstrations. The second one is manual tuning. So if you look at the reward shaping and the curiosity-driven exploration, you want to assign how much do you care about a particular objective, whether it's exploration or reaching goals. Third one is most of these settings are restricted to single task settings, where you care about a particular objective and you train a model for that objective. And most of these settings require a huge number of training samples, which means that you need to train for a long amount of time. So based on this, motivating examples and challenges, I present the objectives of my dissertation. The first one is I want agents that are able to have multitask. What I mean by multitask is that it's not restricted to a single objective, and can handle a variety of natural language inputs. And the second objective is multi-agent control, where I'm able to train algorithms that can autonomously navigate or do tasks in a multi-agent setting. And these algorithms are supposed to be scalable and are efficient to train. And I want to look at this in a partially observable dynamic environment. So based on this, here are the 3 different contributions of my dissertation, which I'm going to list out here. First one is where I look into the long horizon planning challenge, where I create where you would want to decompose tasks based on the natural language instruction. The second one is data-driven exploration, where you would explore unknown environments in an efficient manner. And the third one is scalable navigation, where once you explore something, how would you like navigate efficiently? So let's dive into the first contribution, which is long horizon planning and task decomposition. Going back to the example of the party planning scenario, where you have a natural language instruction given as input, and you have these list of tasks that these agents are supposed to carry out. So this basically involves you creating a list and solving them. So let's take, like, if you as a human being would have to solve it, how would you do it? You would basically have a task that is, and you feed it to a high-level controller, which is your brain. You would say that, hey, these are the different subtasks that I need to solve, which is basically what this high-level controller does. And then once you split the tasks up into smaller subtasks, you have low-level primitive actions or controllers that could solve it. So as a human being, you would, if you choose to navigate, you're going to set up your motor controls and like use your legs to like navigate to it. Or if you want to pick up something, you would say that, okay, I'm going to use my hands to pick up something. So the idea that I'm going to present here is, what if we use language models for this high-level controller? What I mean by large language models is like a famous example of it is ChatGPT, where you can like converse with it. So why do we want to use large language models for planning? So let's take a look at this example where the human instruction is something like, put the bread, tomato, and lettuce in the fridge. And based on this, the language model could reply saying that, hey, I see an apple, bread, and lettuce, and I will pick them up and put them in the fridge for you. What if the instruction was a bit more vague, where you would say, put the groceries in the fridge? Now, based on this question, the robot could reply back saying that I see an apple, bread, and lettuce, which fall under the category of groceries. And I'm going to like do particular actions. So the reason for using language models is that they're pretty good with passing natural language instructions. But the problem with it is that they need some tuning of the inputs to perform effectively in robotic embodied settings. So let's take a look at a few prior approaches that people have used with LLMs for planning, where you have an instruction, you feed it into a planner language model. This planner language model basically gives you a queue of tasks. You basically feed it into a controller now, and then you execute it in the environment, and you get the new observation. So this is quite similar to how you would create your next day plan based on whatever information you have. So, but if you look at this does not really allow for uncertainties. In this case, if you have like a new meeting that shows up the middle of the day, you're not able to accommodate for that, since every event happens after the previous one. And this requires having prior knowledge about what subtasks are actually necessary, which means that you need to know what all events are going to happen the next day before you can plan for it. What happens if we use reactive planning for this to mitigate this? Reactive planning, you have an instruction, you feed it into an actual language model, you feed it into a controller based on the goal that it suggests. You execute that action in the environment, you get the new observation. And based on this new observation, you create a new scene description, which is fed back into the actual language model. And you repeat the whole thing until you get to the end of the episode. Now, if you look at this reacts to the current state, but it does not really allow for long horizon planning, since you're reacting to whatever new state you end up in. And this, like prior works, they rely on an oracle feedback for both the scene description and the completion of subtasks. Now, and also another assumption that people make here is that the low-level controller is assumed to be successful, because we assume that this low-level controller is not that we care about. It's just that like language models are used for high-level planning. So this is where we introduce our method called LLaMAR, which stands for language model-based long horizon planning for multi-agent robotics, where we have an instruction and observation that is fed into a planner language model. This planner language model basically gives you a set of open subtasks, or if I had to put it in simple language, it's basically a to-do list. And basically what it's doing is it's decomposing the instruction into smaller subtasks. Now we feed this into an actual language model. This actual language model is basically going to assign which agent does which action, and keeps track of and ensures that these actions make progress towards the completion of the task. Now you feed these actions into a controller, you execute it in the environment. Now, once you execute it, it's possible that you complete a particular subtask or you do not complete a subtask. So for that, we have a verifier language model, which updates the plan and creates a set of closed subtasks. This, in simple words, closed subtask is basically you checking off things from your to-do list and putting it onto the set of things that you completed. So now the verifier is basically keeping track of things that you have finished, which means that you do not have to rely on an article. You feed this back into the planner language model. Now, the thing is that when you execute an action, it's possible that some actions might fail, which is where we feed that into a character language model. The character language model is basically tasked with reasoning on what went wrong and suggesting corrective actions. And a thing to note here is that the character does not really execute these actions. It's the actor that executes it. It's just that the character is suggesting a hint to the actor language model to improve its actions the next step. And you feed this observation back and you repeat the loop until the end. Let's walk through an example of how LLaMAR would work in an example. So you have the language instruction, fetch the groceries and place them in the fridge. You have memory, which is initialized as null. You have a list of open subtasks, closed subtasks initialized as null. You have previous actions, corrective actions set as null. So you have two robots here, and these are the observations that they see. So on the left side, you can see a tomato and a lettuce. And on the right side, you see the robot seeing the other robot and the stove on the left side and the kitchen, the whole kitchen with the countertops. Now, what happens here is that you feed all of this into the planner language model, and based on these observations and instruction, it's going to spit out saying that the set of open subtasks that are required for this task based on the observations is transport tomato to the fridge and pick lettuce and place it in the fridge. Now, based on this, you feed this into you update the list of open subtasks. You feed it into the actual language model. Now, the actual language model is basically going to predict two actions for these two agents, where agent one is tasked with picking up lettuce, agent two is tasked with navigating to the tomato. And it also creates a memory, which is used for future reference to understand what all things have been executed. Now, what happens here is now once you execute this, things might fail, things might not fail. So for that, we have the corrector and the verifier models, where we feed this actions executed and the new observations into the corrector. Now, if you look at the if you remember what the observation was, the lettuce was far away from it, and that's why the action of picking up lettuce fails. And the corrector is basically able to identify that and suggest that you should maybe first navigate to the lettuce before picking it up. And then the verifier, you feed it in the verifier as well, and you see that you haven't completed the subtask of transporting lettuce to the fridge and tomato to the fridge. So it's just going to say we haven't completed any of these things yet. And you basically repeat this loop until the end of the episode. So to showcase the effectiveness of our approach, we execute this in a set of household robotic tasks where we use the AI to Thor simulator, which is basically a household robotic setting where you have multiple robots carrying out day-to-day tasks. So for that, we introduce MapThor, which stands for Multi-Agent Planning in Thor, which is a simulator, where we define a bunch of tasks, specifically 45 tasks with 5 seats for each. And we categorize them based on the difficulty of the task, where tasks could be as explicit as put bread, tomato, lettuce in the fridge, or it could be as abstract as clear the floor by placing items at their appropriate positions. If you look at this, the difficulty increases as you go down the list. We also benchmark it against a few other language model-based methods. And we define a few metrics to quantify how good these methods are, these algorithms are. So the metrics that we really care about here in MapThar is success rate, which is basically if the task was completed or not. Transport rate, which is fraction of subtasks that was completed. It basically gives you a finer granularity on understanding how much of something was completed. Coverage is basically fraction of relevant objects that you were supposed to interact with, did you actually interact with. Balance, which is a measure of how equitable the subtasks were distributed. Balance is basically the motivation for having this metric was to understand if we have an equal distribution of agents performing actions. Ideally, we would want a scenario where all of the agents are helping towards making progress, rather than just a single agent doing all the tasks and the other agents just piling away. And number of steps, basically how efficient you are in completing something. We also, so since we are working in partially observable settings, we include this exploration heuristic for exploring unknown things. So what happens here is, here's the top view of the room where you have two robots. So if Alice is tasked with exploring the environment, it basically captures images in 4 different directions by rotating in 90 degrees. You feed all these images to a clip image encoder. This clip image encoder basically gives you a dense vector representation of these images. Similarly, the list of open subtasks that the planner predicted earlier, you feed it into a clip text encoder. This clip text encoder is basically giving a dense vector representation of the text. You basically perform a cosine similarity and average them out over the list of all subtasks. And you evaluate the score for each of these, and you explore in the direction that maximizes this cosine similarity. The key intention here is that you want to explore directions that are more relevant to the list of open subtasks. So here's a quick demo of how this looks like. So the human instruction was, I want to put groceries in the fridge. And on the left side, you have Alice transporting tomato to the fridge and lettuce to the fridge. And on the right side, you have Bob picking up the bread and putting it in the fridge. So a few quantitative comparisons. So here's the benchmark where we compare our method, LLaMAR, with a few other methods. So I want you to focus on these 2 things where LLaMAR is able to perform better than other methods across all metrics, basically success rate, transport rate, coverage, and balance. So the key takeaway from these set of experiments is that splitting the problem, the planning problem into different modules helps with better planning and execution. If we compare LLaMAR without vision and with vision, we see that having vision inputs helps as compared to just text inputs. A key reason for that is the corrector module that we have basically requires visual feedback to understand what went wrong. And that basically shows that without vision, you're not able to perform as well as with vision. And with and without exploration, we show that the exploration module helps in like finding objects that you haven't really, that you don't really know where they are. So here's a quick example of the failure correction module, where the task was to put a bowl, mug, and plate in the fridge. The actor suggests pick up plate because it's far. The actor suggests pick up the plate, but it fails because it's far. The corrector module then sees this and reasons that, hey, you failed to pick it up, so you should first navigate to it. And basically the corrective action that is suggested is navigate to the plate. Similarly, another example is once it picks up the plate and it's putting it in the fridge, on the left side, you see the fridge is closed and it's not able to put the plate in the fridge. And on the right side, the corrective action that is suggested is open the fridge before you put it in. So along with this household setting, we perform a few experiments in a search and rescue setting where we have multiple drones in an unknown environment. Each of these drones have a partial observable view of the environment. There are multiple missing people which you need to rescue, which basically means that you need these drones to like go there. You have fires of different types which spread over time. These fires are of 2 different types, Class A and Class B, where Class A can be extinguished only with water and Class B can be extinguished only with sand. And you have these sand and water reservoir where you can pick up something, some resource to like douse it on the fires. So the results in a setting like this, where the human instruction was find missing people and extinguish any fires, is we increase the number of agents and we see that the success rate increases. The reason for that is that as you increase the number of agents, the metrics improve because you have more agents to distribute the tasks in an equitable fashion. So this brings us to a few limitations of our methods. The first one is the computation cost. As you saw, we had 4 different language models being queried at each step, as compared to like other baselines, which just have a single language model being queried. The computation cost is 4 times as that of single module. It's the performance is limited by the underlying language model. As we saw that the language model basically lacks 3D perception. A good way to like mitigate this is basically include a 3D point cloud as inputs to the language model. And there are no guarantees on safety and planning with language models, since it's pretty likely that language models can hallucinate. Like future work could basically address all of that. The exploration module that we used was qualitative. We didn't really have any quantification on how much time would it take to explore something. And the controllers that we used for the low-level actions were assumed to be like really good, which is not the case in real life settings. So in the next part of my thesis, I'm going to address the qualitative exploration limitation and the navigation, the assumption of availability of good navigation modules. So the key takeaways from what we showed with LLaMAR is that we uncover limitations with LLMs for embodied robotics, where we motivate the design for more grounded and feedback-aware planning architectures, which basically leads us to a plan, act, correct, verify framework, which is quite modular and improves the planning. And we also introduced MapThar, which is a systematic evaluation suite, which reveals how task complexity affects the performance of language models. So that was LLaMAR, or task breaker, where you have the task coming in from the left side and splitting it up into multiple subtasks. Let's move on to the next contribution, which is data-driven exploration. I will not be going too much into depth in this topic for the lack of time, but I'm happy to like answer any questions afterwards. So exploration is basically you trying to figure out what regions do you want to explore more and investigate before you make action, just like how Scooby-Doo and his team works. Again, the setting that we work here is we have multiple drones, but this time with limited batteries, which is quite realistic. Each of these drones have partial observability, but with noisy sensors. A reason for using noisy sensors is that the camera that detects or predicts if like whatever it sees, it's generally not 100% accurate. So we assume that there is some error in prediction, and hence we need to take multiple measurements before we can make a guarantee on whether it was good or bad. We introduced mobile charging stations here just because these drones have limited batteries. These charging stations can move along the environment to place themselves at appropriate positions so that these drones can land and recharge themselves. So the approach that we introduced for this is called Batman, which is basically a bi-level approach. Batman stands for Bandit-based tracking, monitoring, and navigation, where we have this environment, and what we do with this is that we first convert it into a grid, where the grid is basically denotes the confidence about information in each cell. So if you are certain about a particular cell, the information that it contains, you will have a higher confidence associated with it. If you are not really confident about what exists in that cell, you would want to take more measurements and increase your confidence. So Batman, basically so what we did was we abstracted a grid world, and once you get this, you would want to so Batman is basically going to ask, what all regions do I want to explore next? And just like how every Batman in all universes has a helper, we have Alfred, who replies back saying, visit these cells that I have calculated for you. And it basically predicts these plus signs on the grid that Batman is supposed to visit next with these drones. The way we do this is that we use multi-armed bandits. Multi-armed bandits are basically historically it comes from the slot machines in casinos where you have multiple arms, you pull an arm and you get a reward out of it, and you do not really know how good or bad a slot machine is until you pull it multiple times and you get a distribution on how good or bad it is. So what we do here is that we use an algorithm called upper confidence bounds, which is a famous multi-armed bandit algorithm, where we have an estimated mean that is updated over as you take more number of measurements. You have an upper confidence which starts at 1. You have a lower confidence which starts at 0. And as you take more measurements, your confidence bounds become smaller, which means that you're more certain about what exists or what is the predicted expected reward from a particular arm. So Alfred is basically choosing which cell out of all of these is going to maximize the probability of cell being interesting for Batman. Now, once Alfred predicts what cells that Batman should visit, it basically is going to ask, how do I get there? And for that, you have Robin replying back that, hey, I'm going to compute the optimal paths for you and predict the paths for both the charging stations and the drones. Now, how do we calculate these optimal paths? We use integer programming, where we have an objective function, which is basically minimize the total time required by Batman to get to goals suggested by Alfred, sorry. You have a few constraints, where the first constraint is that these drones and charging stations should follow physical dynamics. It should not teleport anywhere. It should follow all the laws of physics. It should visit all the target cells suggested by Alfred. It should not collide with any obstacles, which means that it should not visit any cells that have obstacles in it. And these drones should never run out of battery, which means that you need to find appropriate paths for charging stations so that these drones can land on it and recharge themselves. So a quick summary on the pipeline. You have the environment, which is abstracted out to a grid world where you generate confidence bounds based on how much confident you are about a particular cell. You have Alfred, who basically explores the environment and suggests what cells to visit. And then you have Robin, which computes the paths for both the drones and charging stations. And then you repeat this again and again until you have explored the whole environment. A good thing about this pipeline is that since we use multi-armed bandits, which has good theoretical backing, we can give guarantees on how quickly we can compute, we can finish the exploration task with guarantees. And all of this happens in a centralized setting where the explorer and the path planner is basically working in a centralized fashion where it predicts the paths for all the drones and stations. Let's take a look at a simulation where you have these black charging stations. These red cells represent trees with apples on it, and these robots are supposed to take measurements on those cells and understand whether it's interesting or uninteresting. These blue regions indicate water or obstacles where you're not supposed to traverse. And on the lower right side, you have the classification that the drones have made about a particular cell. As you can see here, there's on the lower right, which is 1,6, you have a cell being classified as interesting. And another good thing, a key thing to notice here is that these drones simultaneously land on a charging station, which is at this instance. And on the top right, you have the classification progress. So as you take more measurements, you are able to identify the cells as either interesting or uninteresting. And as you take more measurements, you are able to finish classifying all the cells. Here's a quick hardware demo of this, but with real robots, where you have crazy flies and turtle bots. You can see these turtle bots having these mobile wireless charging systems. You have these no-fly pyramid zones. You have trapped humans, which are these drones are supposed to find. And here's a video of this sped up in 18x. So you can see here that these drones are like flying around and then landing at the same time on the charging station, recharging themselves, and then flying about again. Here's a quick quantitative analysis of what like a few experiments from this, where we compare Batman by increasing the grid size. So as you can see here, we increase the grid size from 5 by 5 to 20 by 20, and the bigger the grid size is, the more compute time you require to solve it. This makes sense because IPs, like the more constraints you have, the more time it takes. And for the large problem, which is 20 by 20, we are not able to find a solution even after 2 hours, which makes sense. So here you have bigger environments need more compute time. Again, we perform another experiment where we increase the number of agents, where we increase the number of drones and charging stations from 5 by 5 to 14 by 7. And you can see here that the total time that is required for exploring or like finding solutions increases with the number of agents. So bigger environments need more compute time. So a few key limitations of Batman is that it's hard to scale with IPs with both grid size and the number of agents, and you require global knowledge about like prior information about where these static obstacles exist, similar to like the Eye of Sauron, where it knows where Frodo exists in Lord of the Rings. So a quick summary of contributions. We showcase that this Batman family helps with good quantitative exploration, and we show that like, using multi-armed bandits can give good guarantees, theoretical guarantees, and we also perform experimental validation on real robots to showcase that it can work in real life settings. So this was Batman, or Misty Mountain Search, where Batman is exploring an unknown environment. Once like LLaMAR calls for exploration when like using the bat signal. Now let's dive into the next contribution, which is scalable navigation. Scalable navigation is basically what would you do when you have a lot of agents and you want to control them together. So we do this using something called multi-agent reinforcement learning. So a quick preview on what reinforcement learning is. It's basically learning desirable behaviors for multiple agents through trial and error. So here in a single agent reinforcement learning setting, you have an environment and an agent. You get an observation, which is what it sees. You feed it into the model. You predict what action the agent is supposed to take. Once you execute that action in the environment, you get a reward based on what objective you are trying to solve. Now, if you do this for multiple agents, this is multi-agent reinforcement learning. So let's take a look at a few prior approaches which have been used for multi-agent appel. So the first one is like the setting that people have used before is they take the ego agent's observation, you concatenate it with every agent's features, and you create a state out of it, and you feed that into the actor network. Now, if you look at this, the state that is fed in as input to the actor network is proportional to the number of agents n. And if you're working in a centralized training, decentralized execution paradigm, you have a centralized critic, which takes in these individual states from all the agents, and you concatenate all of that and feed it into the critic network. Now, this input to the critic network is proportional to the number of like n squared, because each of these Si are proportional to n, and you have n of them. Now, this means that as you increase the number of agents, you would need bigger networks, or you would have to like retrain policies, or the policies that are dependent on the number of agents. So let's take a look at a motivating experiment for this, where we train an RL agent, multi-agent RL agent, where the first model just gets local information, where you just consider the ego agent's observation. The second one is global information, where you concatenate every agent's like observation, that like every agent that exists in the environment. And the third one, where you consider a small neighboring region around the ego agent, and you just consider the features within a certain radius. Now, if you train a model with these three different settings, we see a graph where if you use global information, which is the purple line on the top, you get more rewards as compared to both local and neighborhood information. In practice, like we just have access to local information or just the neighborhood, and we show here that just name concatenation does not really work. So this is where we introduce InforMARL, which basically says that why do we need more information when we can do with less information or just neighborhood information. So initially we have InforMARL, so the first module that we have here is the environment, where let's consider the central drone that we have here. We create a sensing radius circle around itself and connect all the entities that exist in that radius. So now, since each of these agents are connecting to its neighbors, these other agents are also going to connect to these other agents based on their own sensing radius. So what we do with this is that we basically create a graph abstraction of the environment where the entities are represented as nodes. The inter-agent edges are basically communication channels and are bidirectional. The agent to non-agent edges are sensing channels or unidirectional. Now, once we have this graph, we can also have node features associated with it, where each node has a feature corresponding to what it is. So for the ego agent, the node observation could include information like position, velocity, relative position of where it's supposed to go. And like other nodes in this graph could include relative position with respect to I, relative velocity, and so on. So basically, the key takeaway is that we create a graph which is constructed based on its name, where the connections are made based on how close it is, and you have node features associated with each entity. A good thing about this setting is that it accommodates for dynamic graphs, where graphs can connect and disconnect over time. So as you can see here, this graph changes over time. So once we have the environment and we create a graph abstraction out of it, we create a graph neural network out of it, where each of these nodes has a transformer unit along with a multi-layer perceptron added. So this is how a graph neural network would look like based on the graph that we abstracted out from the environment. Now, the first module that we have in InforMARL is information aggregation, where basically it's doing message passing. So what message passing means is that each of these nodes has features associated with it. It passes it to all its neighbors based on its neighborhood. And this is exactly what happens in the forward pass of a neural network, where you have a GNN, which is sending messages to all its neighbors and collecting information from all its neighbors. You aggregate all of that vector using a weighted sum, and that's your aggregated information aggregation vector. Now, if you look at this information aggregation vector is independent of the number of agents. And so what we can do with this is that we can concatenate it with the ego agent's observation. Now, if you look at this whole OI concatenated with X aggregated vector is again independent of number of agents, which means that you can feed it into the actor network and get the action. Now, similar to the information aggregation module, we have a graph information aggregation module, where you perform the forward pass of the graph neural network. You collect all these encoded messages for all the agents. You apply a mean pooling on top of it, and this mean pooling allows you to be independent of number of agents, which means that you can feed this into the centralized critic to train the model. So to summarize, InforMARL is basically you perform graph information. So you create a graph out of your environment, you perform information aggregation on it, which is message passing or sending messages to all your neighbors. You feed that information into an actor network, which predicts what actions the agents are supposed to take. These actions are applied to each agent, and you also you perform a mean pooling on all the agents' messages, and you evaluate how good these actions were for each agent by feeding it into a centralized critic, and you use that feedback to inform future decisions. So this, if you look at this is multi-reinforcement learning, where you have a decentralized actor and a centralized critic. And if you look at this actor and critic are pretty much modular, which means that you can use any of your favorite actor critic methods or actor-based methods. And also the graph information aggregation and information aggregation modules are modular because you can use any message passing algorithm that you have. So we perform our experiments on environments, a few different scenarios where We have the target environment where particular agents are supposed to get to their respective goals. Here it's color-coded. You have the coverage task where the agents are supposed to cover like at least one of these green circles. You have the circle formation, line formation, where these agents are supposed to form a circle and a line respectively. So let's take a look at first set of results, where we showcase how good InforMARL is with respect to sample complexity. So here is like we train InforMARL and a few other baseline algorithms in the target environment for the 3 agents case. So the blue line on the top is InforMARL. The red line right below it is MABPO. See, so these dashed lines are basically algorithms that require global information. And the solid lines are algorithms that require just local information. As you can see here, InforMARL is able to perform as well as MAPPO, despite having access to less information. And it has better sample complexity than most other baselines. You get a similar result for the 10 agent case where you train a model with 10 agents. So the key takeaway is that our algorithm is sample efficient despite having access to less information. The next set of results is scalability. So we train InforMARL with 3 agents and test it out with M agents, where M is weighted from 3 to 15. Now here, you can see that the success rate is consistently 100% among all the different settings. The time that is required for completing the task is 0.97 seconds, which is less than a second. And a thing to note here is that the time that is required to predict each action is less than 0.1 seconds. But a limitation of this is that you have collisions that increases with the number of agents that exist in the environment. The reason for this is that as you add more number of agents, the environment becomes quite congested, and it's harder to find paths that are safe. And the reward function that we used for this just gave a collision penalty, but I think we can improve that if we use more sophisticated methods. So the key takeaway here is that we can scale our method to an arbitrary number of agents, regardless of how many agents we train it on. We also showcase this other set of results where we show scalability in other environments where for coverage, formation, and line, where we train MAPPO with global information, where MAPPO was trained on 3 agents and tested on 3 agents, and trained on 7 and tested on 7, whereas InforMARL with local information was just trained on 3 and tested on 3 and 7. And as you can see here, it's able to perform as well as MAPPO in both the settings. So here's a quick demo of how different formations look like. So here you have these agents forming a circle around this central node. Here's the agents forming a straight line along these 2 different ends. You have the arrow formation and the infinity formation. So a few key limitations of this method is that we trade off with efficiency when we do it in a decentralized fashion. So as you can see here, the agent that is the red agent has to like go to the other side after it gets to know that it's the middle part is occupied by someone else, which might not have been the case if there were a centralized algorithm that told them initially that, hey, you could just directly go there. And this method is prone to collisions. As I said, there's a collision penalty, so these agents collide with each other in some instances. So there have been a few extensions of InforMARL which other people have used InforMARL to like make it better. So the first one is like people have used this with more sophisticated methods to add safety to where they used reachability-based control barrier functions to ensure that these fields do not collide with each other. There's fairness included, where so as you can see here, the objective that was initially used for training InforMARL was more of like you reach the goal as quickly as possible. But in some scenarios, it might not be the case where these behaviors are fair enough for everyone. So we create an algorithm where we try to extract fair behaviors out of this. People have used it for satellite control, where we transfer InforMARL from the simplistic grid world setting to a more complex environment. And there has been a JAX implementation where you can train this model in 5 minutes instead of a few hours. So the summary of contributions for InforMARL is that it's sample efficient. It requires much less samples to train than other comparable methods. You have decentralized execution, and that is performant despite having access to less information. And we create an algorithm that's scalable to an arbitrary number of agents. So that was InforMARL, where we have a whole lot of agents being controlled in a decentralized fashion. So the conclusions for my thesis, or summary of contributions that I made during my dissertation, is that we have LLaMAR, which is the high-level planner, which takes in the human language instruction, uses the plan, act, correct, verify framework. It splits this input task into smaller subtasks, and these smaller subtasks are then based on, like, if you want to explore the environment, if you want to navigate, and so on. And the exploration model that we used in LLaMAR was pretty qualitative, and we did not really have a method of quantifying it. And that's where we introduced Batman, where we have this bi-level approach, which uses multi-agent bandits and integer programming to create paths and look for regions to explore. And we saw that the path planner that we had in Batman was based on integer programming, and it required centralized knowledge about everything. And that's where we introduced InforMARL, which basically does scalable navigation for you in a decentralized fashion. And so we have long horizon planning with LLaMAR, which allows us to handle multiple tasks with flexible natural language inputs. We have exploration with Batman, which allows us efficient exploration in unknown environments. And we have navigation with scalable multi-agent control and efficient training. So that was my dissertation. And most of this work was not possible without this band called Siddharth Nayak's Club Band, and with a little help of my friends. And I would like to thank all of you who helped me with this. So just so that you don't have to perform, you guys don't have to perform, would not have to perform a multi-agent exploration in this image, I'm going to point out where you exist in this environment in the next few slides. So first of all, I would like to thank Hamza for being a great mentor, advisor, and more importantly, a nice human being. The freedom that she gave me for exploring different research topics at the beginning of my grad school was really nice. She also made sure that my first year of grad school, which was during COVID, was without any issues. Next, I would like to thank my committee, Luca and Claire, for taking out time from their schedules to give me valuable advice during the committee meetings, outside the committee meetings, and to ensure that my dissertation was up to a good standard. And also Luca for the visual navigation class that he taught during my second year of grad school, which I learned a lot and was quite awesome. Next, I would like to thank Karthik, who was a reader on my thesis, with whom I collaborated on InforMARL and LLaMAR. He was my first point of contact at MIT when I joined Hamza's lab during COVID, and he ensured that my transition to grad school was smooth. So he was the one who basically motivated me to explore new topics that I was not really familiar with. His advice in avoiding like common mistakes in grad school was really valuable. So thanks a lot for all your help. Abraham, who is also a reader on my committee, who was my internship advisor at MUL, and with whom I worked closely on the Batman project. He gave me like enough freedom to explore different approaches for the project before we finalized on what I showed today at the presentation. It was a pleasure working with you, Abraham. Then I would like to thank Anuj, James, Erob, and Brian, with whom I collaborated on the LLaMAR project. Their feedback on how to use language models and get better outputs was really helpful. Marcus and Stefano, with whom I collaborated on the Batman project, and Anup, with whom I worked during my second internship at MUL. My undergrad advisors, Harshad, Professor Ravi, and Abhishek. Without their help and mentorship during my undergrad, I would not have been here at MIT. Next, I would like to thank Jasmine and Sydney, who have been the most amazing lab mates, collaborators, and friends. I got to work on quite a few projects with you guys and learned quite a lot. Chris, Luke, Kendrick, and Mike, with whom I worked on my first research project at MIT during my SM. Aditya, with whom I worked on the LLaMAR project and have been continuing on a few other projects and extensions of LLaMAR. I hope our collaborations go on for a few more years. Yevon, with whom I worked on a project related to healthcare, which started as a class project and then led to a NeurIPS paper. My first two UROPs, Kenneth and Helen, without whom the InforMARL baselines that you saw today in the project would not exist. Adelmo, Marina, Vittal, Jackson, and Darren, without whom LLaMAR would not exist. I got to learn so much from you guys. You were really awesome. Simran, Akila, Carson, and Daniel, who I mentored for their MNG thesis. It was an honor to work with you guys. Rebecca and Tony, my first two friends at MIT, without whom I would not have learned as much as I did from my classes during first year of grad school. All the pieces and projects that we did together, it was really helpful. My lab mates, Max, Sandeep, TT, Jeffrey, Victor, Alyssa, Alan, Shashank, and Jules. You guys made working in the lab quite fun. My friends who ensured that my life outside research and academics was fun and enjoyable: Kyle, Ashutosh, Siddhant, Mansi, here, Nishkam, Richa, Keshav, Satvik, Mrigi, Naman, Dimple, Prajna, Philip, and Avik. My aunt and her family, who made sure that I felt at home when I moved to the Boston area, and gave me nice homemade food. Sorry, Pranav, I could not really find your photo, so you're not there in the photo. Finally, my dad, mom, and my sister Apurva, who have been a constant pillar of support throughout my life. They have cheered me through every accomplishment, setback, and acted as my sounding board and reassured me with their boundless love. I did not have enough space to put everyone in this image, but I would also like to thank my collaborators, Yashan, Arvind, Marze, Sanjat, Matt, Sanjeev, Lay, and William and Joseph. My cricket club teammates, Manu, Ani, Pradeep, Abhinav, Vaibhav, Aditya, Ishan, Harshad, Manraj, Mihir, Shivam, Sayog, Ronak, Anish, and other friends, Akshay, Anurag, Abhishek, Aditya, Anaga, Shreya, Harsh, Karan, Advait, Aniket, Harshad, Somesh, Soumya, Rajat, Anand, Vineet, and Kamran. Thank you.
Thank you, Siddharth. So we'll have question and answers. Let's start with your committee. I would suggest we start with the people on Zoom.
Yep.
And then move to get Google and me, and then.
Yep, sounds good.
I suggest somebody to
Mhm.
something.
Yeah, repeat. Yeah. Claire, do you want to start?
So we have a session after this, right? Where we can go into more detail in terms of questions. So right now we're asking kind of a high level questions. Perhaps. I don't hear you at all, Hamza.
I think what she's saying is that
The AeroAstro processes we ask now.
Oh,
It's
okay.
a session. Yeah.
Okay. Okay, thank you very much, Siddharth. That was a really nice talk, a kind of synthesis of things that some of which I've seen before and some of the newer work that you've done since the last meeting. I have a couple of maybe more detailed questions, or maybe more, I don't know how to call them, more, questions on specific points, and then a couple of high-level questions. The first question is about, as you were presenting LLaMAR, you talked about, and you showed some results about how some of the performance metrics that you were evaluating, those quantitative, those metrics, not necessarily quantitative, but they tend to improve over as you scale to larger numbers of robots. And that it makes sense on one hand, but on the other hand, I believe you mentioned this, but the the safety aspect. So the numbers of possible conflicts between agents
Yes.
would increase. And I
Yep.
just wanted you to maybe comment about,
Yes.
just about the collision avoidance and safety aspect,
Yep.
just focusing on LLaMAR as you're scaling to large numbers of robots.
Yes. So the result that I showed here that's visible on the slide right now was for the search and rescue setting, where we increased the number of agents from 1 to 5. The environment here was pretty widespread, which means that there was enough space for all the agents to navigate. But we also did this with in the MapThar setting and in the household setting. So this is the slide that shows that, where we increase the number of agents from 1 to 5. And as we see here, that the success rate initially increases as we increase from 1 to 3, but then it decreases after 3. The reason for that is exactly as you pointed out, where the agents are not able to find good paths without collisions. And that is like, the reason for that is again, like the room is pretty small. So there aren't like sufficiently enough number of paths that these agents can take. So I think like the point that you made here is that adding safety filters is really important. And I do acknowledge that it's a limitation with using language models for these kind of tasks.
And that may be a topic of future consideration, right?
Yes.
For
Yes.
maybe you could just extrapolate a bit and think about, incorporating constraints like this, or maybe model-based constraints into
Yep.
an LLM framework.
Yep.
If you could talk a little bit about the prospects of that.
Yeah. So I think one approach that like we could do here is so since we used pre-trained models that we for these experiments, there was no way of like specifying hard constraints or making sure that these the data that these language models were trained on knew what safety was. So like an initial approach to like solve this would be to curate a data set where we use some of the model-based methods for training or fine-tuning an existing language model to include all these safeties, and also add like a safety filters before the execution of the actions to ensure that these actions suggested by the language models make sense from an execution perspective. So basically training or fine-tuning language models based on more safety related data sets, and adding a safety filter outside before the execution layer to ensure that these agents the LLM agents are not hallucinating.
Could you also talk a little bit about, in the LLaMAR framework, the incorporation of feedback? And I think you mentioned it, but I didn't catch it. So how does one incorporate, say, state feedback into this framework?
So so here we have, so let me show the slide, I guess. So here the action is executed, and there's also like so the connector knows the input from the actor, which is like it attempted to pick up a plate, but it failed because that execution like was not able to like, so the state transition from picking up the plate before and after did not really happen. And the image feedback that it gets is that the plate still exists on the table and not in the hands. So it uses that visual feedback to understand that this action has been, whether that action has been successfully executed or not. And that's how it like basically suggests a corrective action if it is required or not required. And the suitable feedback is provided based on what kind of errors happen in the execution of the action. So it's more of like a visual feedback.
And maybe you could comment on the time frame of that. So as it plays out, at what point does it recognize that it's not going to make it and then correct the action?
So it execute like the actor. So the assumption here is that the actor tries to attempt an action and it does not really work. So if I'm like really far away from the plate and I attempt to pick it up, the robot, basically what it does, or the low-level controller that we had here, was that it can only pick up something if it's within like 0.5 meters from away from the robot. So it tries to like pick it up, but it fails in the sense that the action itself does not really happen in the environment. Like physically, like it does not really like get through.
So would you actually see it grasping for something in the air and then, it realizes, or is it correcting it as it's
something,
reaching? Okay.
Yep. So it tries to like grasp it, but it fails. And then, I mean, there's nothing to like grasp right next to it. And that's how it understands that something failed.
Okay. One more question about your multi-arm bandit work in Batman. Could you just say a little bit more about, how the choice of the next grid cells to explore depend on what you already know about the graph in that framework?
Yeah. So here what's happening is you have a centralized Alfred, which is basically keeping track of the cells that it has, like the confidence of each cell. So it's basically a global view of like what things have I seen in a particular cell and a map of it in some way. So the decision of like what cells to explore next is just based on whatever information you have collected up till now. And it's possible that like you might suggest that something is, you feel that something is interesting and you suggest that cell. And when you go there, you see that it's not interesting. So the confidence for that like increases where you know that it's uninteresting. So as you take more measurements, the more confident you become, and you would not want to explore that particular region anymore once you cross a certain threshold.
So how specifically, how do you balance that exploration versus kind of, focusing in on what you already know and trying to really zero in on cells that are near the goal or avoiding some obstacles?
Yeah, so here the objective is to not just find the interesting cells. It's more of like being able to classify all the cells as well, either interesting or uninteresting. So we are not like trying to figure out like we need to find the interesting cells, just the interesting cells. It's just that we want to classify all of them, but we also want to ensure that the more interesting cells are classified first before the uninteresting cells are classified. So the idea here is that you don't want to spend a lot of time taking a lot of measurements in the uninteresting cells.
Okay.
So yeah,
Do the cells change over time?
these cells don't change over time. It's the environment is static in the sense that the interesting cells are just static.
Okay. But they could change over time.
They could change over time, yes.
So you would need something in order to make a similar guarantee. You would need to have something about the time constant of exploration compared to the time constant of changing, for example.
Yes. I think like in that scenario, you could have a belief of the grid that updates over time as you take new measurements. But in that case, like as the environment is changing over time, you might have to like retake measurements in the cells that you initially thought were interesting after after crossing a certain threshold.
Okay, and then relevant to the plot that you're showing right now, what guarantees can you make about like the ability, you mentioned this, but I'd like to ask in more detail, the ability to get a control action that's useful in real time, and the time that you actually have to execute that.
Sorry, could you repeat the question?
Yeah, I'm interested in the kinds of guarantees that you can get from this Batman algorithm in terms of the ability to get useful information in the short time that you have to before you have to take your next control action or your next step.
You mean like just exploring something and then you don't want to explore, like something like that?
Well, no, I mean, well, maybe. I mean, like the real-time guarantees on being able to get useful information in real time as you need it, given the time constant of like the system moving, the system dynamics.
Yeah, so here, once we task with these agents to like explore something, we are basically performing the whole, like in this particular like set of experiments, we perform the classification of all the cells, but it's possible that you do not want to wait until the classification of all the cells. So in that setting, like a good thing about using bandits is that you have a measure of how confident you are about a particular cell. And the setting that we used here was that we had noisy sensors, which means that you need to take multiple measurements. But if you had like a really good sensor, then that means that you are able to like classify things at a much faster rate. So let me show a graph that shows how things change when you change the sensor accuracy. So as you make the sensor worse, which is the blue line, and as you make the sensor more like accurate, which is like 1 here, you are able to like identify things much faster when you have like really good sensor. So we show here that like within 5 decision steps, we are able to classify all the interesting cells. Whereas when the sensor gets worse, you need like around 150 high-level decision steps. So if we have like a particular threshold on how much do we care about things being classified, then I think this gives us a good framework to quantify that.
Maybe I'll just ask one more question at this point, which is a higher level question. You've got a lot of motivation, which is related to some of the examples you've shown in search and search and rescue, for example. One of the motivations that you talk about is this advanced air mobility, incorporating drones into the air traffic system for, say, delivery or other purposes. Can you maybe just talk a little bit about how you see your algorithms playing into that application? Maybe a little bit about the trade-off between a centralized versus a decentralized framework there.
Yep. So in InforMARL, we showed that you can do better. I mean, you can do as good as algorithms with centralized knowledge, as long as you are able to get information from your local neighborhood. I think that framework allows you to get good scalable control, like control mechanisms for multiple drones. And the extensions that people have worked on where you add a safety filter to ensure that things don't collide is something that can allow us to get really scalable methods in a decentralized fashion. Whereas in a centralized setting, you would have to share all of the information that each agent sees to like a centralized controller, and then the centralized controller creates a plan or like the next action for all the agents, and there's a lot of communication, which means that as the number of agents increase, with a limited communication bandwidth, you are going to be restricted because like based on how much bandwidth do you have for those centralized to agent communication settings.
So right now, what are the limitations of applying such a framework into a scenario which involves, incorporating it in the air traffic system?
Yep. So right now, like the limitations are that you are losing out on some efficiency because you're working in a decentralized fashion. You are also like in the base setting that I showcased here, you are restricted by not having guarantees on safety at all instances. So like once we can like work out the next parts of InforMARL where we can guarantee safety, I think that's when it would be a good algorithm to apply onto like real drones, because we don't want drones to like collide with anyone with a certain guarantee. So I think like loss on efficiency and safety guarantees is like a limitation that is not allowing us to apply this onto these drones.
Okay, Thank you, Siddharth.
Thank you. Karthik, do you want to go next?
Yeah, thanks a lot, Siddharth, for the really nice presentation summarizing all your work over the 5 years. I think what really stands out to me is the number of extensions that have come out of your work, which I think many people in the lab and elsewhere are also pursuing.
Yep.
And so I have a few questions on the LLaMAR part, and we can maybe start there. I wanted to get a sense of what's the potential or role for a more classical optimization-based approach to allocate tasks to these agents. So the parallel I'm thinking of is essentially if I build up this memory over time, I do have the notion of where certain objects are, and then I have multiple agents. So isn't something like a vehicle routing problem sort of module potentially useful there? And if so, like, yeah, how do you think about incorporating this?
So that's a good point. So if you know what task you are trying to solve with these robots, like if you have a repetitive task, then you can use these classical methods, vehicle routing problem, like solutions to that, which will, I think, give better solutions than what LLaMAR does. The advantage of using LLaMAR is that it's more generalizable from a perspective of being useful for general public, where they can just give a natural language and then can have these language models formulate what needs to be done. But if you want like really specialized solutions, I think for like a particular application, then I think using specialized integer programs or specialized objective functions to solve them is a better way to like get those systems working.
Maybe I'll follow up here. So I'm actually not thinking about a specialized application, but I'm still thinking about the fact that LLaMAR builds up this memory over time, right? And the memory holds information on known locations, right? And at that point, do I still want to use the LLM to make use of that known information, or is there like a way in which we can use some of these other...
I think if we are able to translate all of that memory to an objective function plus constraints formulation, then I think it's a good way to like solve it and not rely on LLMs to do all the planning, because now you have like an objective that you know that it's going to be optimized for, and these LLMs are basically trying to like do things as quickly as possible, but there's also like things that it does not really guarantee things being correct at all instances. So I think if we build a memory over time and then use that to formulate or translate that to an objective function plus constraints, then I think it's better to like stick to those methods.
Can you actually also share some more details about the training for LLaMAR? In particular, like how this might scale as we have more agents, or do you think...
Yes.
Yeah.
So your question is more of like, if you scale to more agents, how would you ensure that things work as well as before? Is that correct?
Also more about the training process itself, and like what are some of the challenges that we would have in the training?
Yeah, I think from a training perspective, when you have more number of agents, it's possible that you can get super linear performance as you have more agents when you use good optimized solutions. But it's not the case when you just take a language model and copy it to like multiple agents. So I think data sets that involve interactions with multiple agents could be used for those kind of solutions, where you would want to extract like more performance-based objectives while executing. So I think like data sets which have like more interactions and you understand like this agent's action affects this other agent, and then that affects someone else. And then how do these interactions play along, and how could you have done if the agents took some other actions? So more of like non-stationarity being like look into more details. So I think that is something which we could try out in the future.
Right. Moving on to the Batman piece of your work. So is in your hardware experiments, did you declare something as interesting or not based on a vision model? Is that
Yes. So on the left side, you have like this camera, like computer vision doing on some online sensing on whether something is interesting or not. So we have like a detector module which is trained on detecting whether something is interesting or not. But as every detection module has some sort of like errors associated with it, where you have like true positives and false positives. So even if you have false positives, this is robust to that because you take multiple measurements, and it's very unlikely that you take multiple false positives in the same cell.
And just to get a sense of the numbers, like how many times do you typically have to visit a cell, like maybe in this exact example, right, to have the required confidence? And I'm guessing that's also a tunable parameter.
Yeah, so here, like in this simulation, which is like the ROS simulation, as you can see here, the number of visits that is required is, I guess, like around, so let's I don't really have it at the top of my mind, but this cell is visited twice, thrice, 4, 5, and 5, 6, 7, 8. Yeah, after 8 visits, it classifies it that this as interesting. So yeah, like around 8 to 10 visits. But I think that's more dependent on how good or bad your sensor is, like how much confident you are about it. So the more confident you are, the lesser number of visits you will have to make in a particular cell.
Right. And maybe the last question I have for now is with InforMARL, so is this intuition correct that the true limit on scaling to multiple agents is just the congestion that gets created? So if you actually have a bigger and bigger environment, which with an increasing number of agents such that the density remains constant, then we would be able to like scale this to a lot more agents without loss in performance.
So it depends. So when you mean performance, there are two things. One is like reaching goals as quickly as possible. And as I showed in this example where let me open it up. So this example where you're forming a line, this central agent, like it goes to the center and then it goes somewhere else. So if it's like more like a coverage problem, then I think centralized methods are obviously better because you can assign which agent goes where. In a decentralized setting, I think you will always have to figure out what happens once you get close enough to that position. So as you said, like if it's like really decongested, I think it scales pretty well. So this work. So this work basically scales it to like 1,000 agents, and they show that it does pretty well to a certain extent when you have like a really decongested environment.
Thanks.
Yep. Abraham, do you want to go next?
Thank you, Siddharth, for the talk. I think all in all, it's been amazing collaborating with you. I enjoyed the time you had with Merle as well. And this presentation also, I think you have done a good job synthesizing information across the board. Maybe since you already had InforMARL, I'll ask a question about this and then go back to a couple of questions I had on LLaMAR. When you do decentralized planning, I think one problem typically one faces is deadlocks, where you could have multiple agents trying to go to each other opposite directions and they are blocked by their respective agents. Can you comment a bit on how your approach handles that? Is that possible?
So like all of the policy is controlled by the reward function that it's trying to optimize for. As you pointed out, that when it has deadlocks, like the reward function that we used here, it just like goes and collides with it. But I
see.
think like the safety filters that we have as extensions takes care of that. So this particular work, this one, the recent paper, it basically chooses one of the agents to like move forward before letting the other agent go through. So whenever it seems that there's a deadlock, I think one of the agents will have some preference given based on. I haven't read the paper, but there's some prioritization that happens in here.
So I'm wondering also, like in the higher level plan of your original graph neural network, is there something that can be learned to prevent plans for individual agents that will create deadlocks? Is that a possibility, or is it something just because of decentralized nature is not a possibility?
So here it's like not creating plans per se. It's more of like it's just reacting to where it's supposed to go based on the current state. So it's technically not planning like few steps ahead, saying that I'm going to collide with someone else, so I'll just create a different path. It's just reacting to like what it sees and tries to optimize for the reward. So I think a good way to like mitigate like what you said was basically have a prediction module that predicts how far, like if you follow this action, how far ahead would you go based on the same policy, and then use that extension to like in an MPC fashion where you use that to like prevent collisions or like deadlocks and so on.
Okay, I see. All right. Then I had a couple of questions on the LLaMAR side. One was, I think it was in slide 32, where you gave a good example on why you need a character module. Can you also elaborate a bit on why you separated in your design choice on between a planner LLM and a character module? In my mind, the planner LLM should be able to take that into the corrections into account, no?
So that's a good question. So when we initially tried this out, we had all 4 modules added on to a single like LLM. Like we tasked the LLM to like give all of these outputs, and when it tries to do that, it does not really give good outputs because it gets confused with what it's supposed to output. So that's why we had to like make this distinction where each task is associated with a different LLM. Like when we worked on this, we didn't really know like what the term for this is called, but now it's called agentic frameworks. So yeah, this is more of like LLMs being set up in an agentic framework to distribute things like what it's supposed to do in a more performant way. So like the reason for that is basically LLMs not good at just predicting all of it together, and also the inputs that it needs for those particular things is quite like important. So here for the planner, it just requires observations and like what it sees. But for the character, it requires the previous state and the next state. So if you give all of that, the input size becomes very big, which means that the context size, the context window that we used for the language model gets filled up pretty quickly. So another limitation of LLaMAR is that like when we worked on this, the context size got filled up really quickly with the information about like all the state like agents. Now I think the context sizes have gotten bigger with better language models, and yeah, I think now we kind of think it's better.
Okay. So I agree with you that like having a single LLM do everything might be too much, and I think the way you have decided to split the roles of each LLM makes sense. So I agree that you should have probably a planner LLM, an actor LLM, and maybe a verifier LLM. Just
So
to follow up on that, like, what I'm not yet sure is, can you go back to the, I think maybe a couple of slides back where you had like the entire flow chart.
Okay. You mean this one? Oops. This one?
Yes, this one. So, like, this is where I was basically not sure. Like, I guess between planner LLM and a character LLM, you need that separation so that character LLM just focuses on producing the corrective action and therefore can
Yes.
only depend on the previous observation,
Yes.
whereas the planner LLM keeps track of the high level task. Is that what you're
Yes.
saying?
Yes. Yes.
I see. Okay. So because both these actions are still going back to the planner LLM, the planner LLM's output keeps in mind that things that it previously suggested were
Yeah.
correct.
Yes.
I see. Okay.
And also the actor LLM, it takes that feedback to understand that this is what went wrong.
Okay.
So yeah. So planner LLM does not really execute, it just creates plans.
Right.
It's more high level, but the actor is the one who actually goes in and like executes things.
Got it. Okay. And then one more question that I had on this topic was, I think you mentioned that you are assuming that the low-level controller is good, which is reasonable. Like you are saying that whatever you task it is good.
Yep.
But I guess there's also an implicit assumption that the actor LLM comes up with the right task for the low-level controller.
Yeah, it could come up with the right task for the low-level controller, but the preconditions required for that action might not be satisfied. Like in the example that I showed, where the plate was really far away, it could not really perform that action.
Yeah, but I think what I was thinking more is that for the same plate example, let's say your low-level controller is something that can grasp an object at a particular height.
Yeah.
Your actor LLM now not only needs to pick up the plate, but the plate is over here, so go there and pick up.
Yeah, but then it's combination of two different actions, and I guess it's more of like, how do you define the action space?
Okay.
The action space that we had was something like this, where the navigations are restricted to move, rotate, look up, look down, and navigate to like a particular position. And the interaction objects are more of like pick up, put, open, close, slice, and so on. So you cannot really combine two different actions for like a particular subtask. So the whole idea of having an actor language model is that it can decompose the individual actions required, the high-level actions required for completing a particular subtask.
I see. Okay, so in this scenario, when you say pick up the plate, that low-level controller automatically identifies where the plate is, and if the robot is nearby, it automatically identifies where the plate is and picks it up in the right way.
Yeah, but if it's really far away and it cannot really see, then it first has to navigate to it before attempting to pick it up. That's like
what I was more worried is like the case where that low-level, I guess that's where you assume the low-level controller is good. Like it could happen that even if we say the robot is nearby and it sees the plate and it can pick it up, it may not do it in a proper way that the plate is dropped, for example. So you're assuming that never happens.
That doesn't happen.
Yeah. Okay.
So we had to make some assumptions on like how good, because like then you go down the path of like creating a grasping algorithm that's like really good. That leads to a different thesis.
And I think this is maybe in line of what Karthik was asking earlier. Like, I guess these tasks could internally be something that could be based on optimization-based control or something. Like, those could internally be trained or designed such a way that they do well. And then you have a LLaMAR acting sort of as a conductor, orchestrating different modules, I guess.
That makes sense.
Well, thank you for the presentation and answering the questions.
Thank you. Thank you. And also, you did an amazing job with the slides. Thank you. You see pretty well. Thank you. Yep. So that what I can Yeah. So the initial open set of open subtasks is more of like what it sees, and now once it gets closer to the fridge, then the planner is updating the open subtask and like open the fridge before doing it. So the planner, so the whole reason why we have the planner is basically updating the list of open subtasks based on new observations that you get, and it's not fixed right at the beginning of whatever seat, because now as they explore more about the environment, now in this view you don't really see the fridge. Now it has to also explore where the fridge is, and once it explores it, the planner also puts in that open the fridge as well. But again, the limitations here is that the controllers that we use are assumed to be good enough to like solve something, but so geometrically it does not really have to figure out like I need to like move the hand, like I need to be like in a certain orientation to open the fridge. If it's like if this is the fridge and I'm like this, I can open the fridge. I don't need to be like in a particular orientation to like get move it. So that's like a limitation, I think, where you do not really care about the low level actions, but it's more of like high level planning. You need to like add more things. So this is not an end-to-end solution. There's like a lot of nitty-gritty details that needs to be taken care of.
Also for the
Yep. Yep. So we set a certain threshold where if it's like within a certain distance and it's able to interact with it, we just stop. We don't. Yeah. I think that's like yes. Yeah, like keeping track of like things, and that's something that one of my managers is working on, where you basically create a map based on how much you explored, and that allows you to like geometrically place yourself accordingly. So that's like an extension that one of my managers is working on. Yes, the map representation will add on to it, and he basically shows that that helps improve the performance when you have like this global map that is updated in a SLAM fashion. I think he just gives the image along with like the top-down view, the map that he creates. And like he tried out two different approaches where the map is given as an image and also as a tensor, where the tensor is basically 0, 1 kind of where the channels are where objects exist, and 0 and 1 basically represent whether it exists or not. And he shows that the image input is better than the tensor input. Yep. Yep. Because so the advantage here is that the Bandit algorithm allows you to be like more data driven. And since we assume that the sensor is uncertain, that allows us to model the uncertainty on how good or bad a measurement is and how confident you are about a particular cell. Now, including that in an individual program might be possible. We probably didn't take a look at like formulating it. I think it's possible, but I think it might just complicate the number of things you would add in the programming. Yeah. Yep. Yeah.
I'm mindful of the time, so I'm
Yep.
going to ask two sort of very high level questions. The first had, they're actually related, so maybe it's one question I'll ask. You pointed out that one of the issues with LLaMAR is the hallucination issue.
Yep.
So can you sort of say what would go wrong? Like where does it break?
Where does it break?
Then Related to that is the two examples between the household robotics environment and search and rescue. Those seem like really they are very, very different
Yep.
tasks. And
Yep.
so comment on, you said it's a very generalizable framework. So
Yep.
can you comment on what's easy, what's hard, and those two?
Yeah, so first question about the failure cases, like there's a lot of things that goes wrong with prediction. So I'm sorry I don't have like a good visual representation of this, but like the first thing is that the LLMs misgeneralize on how much of an abstraction do I have with regards to the action space. So when we task the agent to clean the dishes, it basically goes and puts the dish in the sink, uses soap and water to like clean it, like picks up the soap, turns on the faucet, and then cleans it. But like it could have just used the clean object action that we gave it, but it did not really use that. So that's like a misgeneralization on the action space. There's also like limited spatial reasoning that I talked about earlier. And also we use, so I didn't mention this in the slides, but we use SentenceBird to translate natural language to executable actions. So what's happening here is basically we allow the language model to predict in a free from language form, and we convert it into a fixed function. So there's some mismatch on that as well, because it thinks that something exists, but it doesn't exist. So in this case, it suggests that maybe navigate to cabinet 1, but cabinet 1 does not really exist. There's only cabinet 2. So I think there's a lot of hallucination in those settings as well, which is one of the failure cases that we have here. I don't have the failure cases slide for the search and rescue in my backup, but again, like similar things happen where it's not able to understand how much abstraction do I have, how much, like what kind of access do I have with regards to the action space. The second question was more about differences in the environment in the search and rescue and the MapThar setting. Like on a high level, both of them, we wanted to show what happens when we give a high level instruction and if it's able to like parse it into more like good subtasks. From an execution point of view, I think we were able to come up with more natural language tasks for the MapThar setting because it's easier to define tasks. Whereas in the search and rescue setting, the instructions were pretty vague. We just had to tell that, hey, you need to like extinguish the fires and like find these missing people. We could not really come up with a bunch of like a variety of like scenarios. So we just came up with 5 different settings where we could like do a permutation on what is activated and what is not activated. So I think the flexibility with testing out with more realistic, like more variety of scenarios was possible in MapThar, which was not the case in the search and rescue setting.
Need to know the specifics.
Yes. Yep.
It's pretty much open.
Yep. Yes.
And,
Yeah. Makes sense. Yep.
Good sense of
Yes. So I think like that's what we were trying to like see initially, and that's what led to the sequence of experiments that we did. So we initially tried it on household settings because we knew that these LLMs have seen these household settings somewhere on the internet, whereas search and rescue are like more abstract, and we need to see if that works there, and it worked well to like certain degree. And yeah, like this also brings us to the question on the success rates that we had for our methods. It was just 66%. I think there's a lot of room for improvement with improving and making it better for like real life implementation. So I think the point that Luca mentioned here for real life execution, I think we need to like consider all of that to make this 0.6 closer to 1. Okay. Okay, yeah. Sounds good.
Claire,
I think
Pranav and Karthik, I sent an email with a different link. Luca and I'll just join that in a minute. Yeah.
All right.
We'll see you.
A mic to that. Let me do that. Is it better? Can you hear?
Yeah.
Okay. So there's Stairway to Autonomy, which is a reference to Stairway to Heaven. There's let me like show the art as well. So then there's Stopbreaker, which is a reference to Heartbreaker by Led Zeppelin. It's also a reference to Dark Side of the Moon, which is the triangle and the rainbow thing. So that's 3. There's Misty Mountain Search, which stands for Misty Mountain Hop, the song by Led Zeppelin. But it's also a reference to a lot of the rings, which I also made in the slide. Sarah. That's 4. And then Whole Lot of Agents is about Whole Lot of Love from Led Zeppelin. And you have these classic Zeppelin from Led Zeppelin. And then this is, I made 2 references here, which was Sgt. Pepper's Lonely Hearts Club Band. And I also said with a little help from my friends, which is the second song from the album. Yeah, so these are the references, I think. Yeah, I need food. Yeah, I'm gonna stop sharing, I guess. If anyone wants a copy of this. Yeah.
Like using like a sample information, local information, and then outperform things that you promote local information.
Yep.
So can you help me understand more? It would be like what is the mechanism in your architecture that is letting you outperform local?
It's not outperforming, it's just that it's performing as well as the other one. It's just that you can do better with this local. So when you're in a navigation setting where you have a lot of agents navigating, you do not really care about an agent that's like 5 kilometers away from me, because that agent is not going to affect any decision that I make. I only care about the things that I see next to me for my own decisions. And that's what allows us to like just be good with that like local neighborhood information. We also do this experiment where we change the radius of like how much information do we want to consider. So we increase the radius from 0.1 to 5, and then global. So we show here that having a radius. So you see here that the radius increases from 0.2 to 0.5. You have a big jump. So that basically tells us that that radius is where you would like, that is the radius that you care about. Anything bigger than that, you did not really gain much out of it. So
Sorry, follow-up. You also said that you are doing a side experiment with an MN about including math.
yes, that's not for this one, it's for the first piece.
Wonderful.
Yeah, I'll eat up. I think.
I don't think there's any food left with more on this video channel.
No, I think Hamsa will be here in a bit, so I'll probably wait.
complexity you want. So in one slide, you have four kinds that for your image space and then for your task space.
Yes.
And then you use that to decide which direction you should explore for.
Yes.
So I was wondering, let's say you have a task space, put letters in the bridge.
Yeah.
But the letters is not like let's say the letters is in a drawer, so the letters is not in any bridge.
Yeah.
But the times of writing matching for that would probably send you to the bridge first because it has
Yeah. Yep.
So that
So the thing is that we also like average it across all the subtasks. The idea here is that the clip model is also trained on a large multimodal set. So that it basically knows that lettuces are more like probable to be found in fridges or like tables or like drawers as compared to like maybe a trash can or like I don't know a sofa. So that assumption allows us to like lead us to good regions. But again, as you said, it's possible that it goes to a different region that's not where it's not likely to like be where you would find a lettuce. And that's basically what led us to the second piece where we have qualitative exploration and then we have quantitative exploration. So yeah, so that's like we are good with just using this, like having this assumption.
I guess then I have a related question. Nobody else asked me questions, right? You go. This is the first time I paid attention to what you're doing.
I wonder. They have questions.
Great presentation.
Thank you.
Question about the third one.
Yeah.
Are the actor networks also shared or like the complete?
So actor is decentralized, completely decentralized. So every agent is taking action for itself based on whatever it sees and whatever information it gets from its neighborhood. The critic is shared, but while executing, you don't really need it. So critic is like collecting all the global information and making sure that everything is coherent. But the actor allows us to be decentralized.
The one critic for each local neighborhood, the one critic for the.
One critic for all agents, like one critic to rule all.
How do you decide what's the name of the robot?
I just did Alice, Bob, Charlie, Dirk, like ABCD. I think that's what most people use in the literature. So I just kept up with the same naming system. Yep.
I just want to say your slides are absolutely amazing.
Thank you.
I love.
Thank you.
I guess it's a follow-up question on what we were talking about in this slide for the clip encoder. So like for something like a kitchen, I think as your guys have mentioned, it's relatively more straightforward for where you would likely find things. But if you, let's say, have a more complex environment, like maybe a wet lab synthesis,
Yeah.
when you're
Yep.
trying to synthesize some then in that case, then how would your methodology transfer over to those types of environments? Like, would you need more fine-tuned?
Yeah, I think you would need more fine tune because there's no guarantee that these things have been like the LLMs have seen these kind of data points. So I think fine tuning is necessary, I guess. Does that answer your question?
Yeah.
Okay.
How do you stop the LLMs from like gaslighting each other?
So there's only one language model which is controlling all the agents.
No, but if the,
Oh, you mean the different modules from gaslighting each other?
so the higher LLM from like gaslighting.
Yeah, so it's possible they do that. We haven't seen scenarios, but I think one of the papers that I linked previously showcased that it's possible that these LLMs can hallucinate and build off of each other's hallucination. Yeah, it's possible. We haven't seen something like that, but it's possible. That's a good question.
What are you doing next?
I'm going to California under Lens of reference. I'm joining Waymo to work on their vision language models team to make for edge case detection. where things that have been trained, like the model has been trained on certain data set. Now, what would happen if there's something that's not trained, like something that happens which is not in the data set? How would you react to it? That's something that they want to like focus on, with the tail scenario and self-driving scenarios. That's where I'll be going next.
I think they also use LLM.
They don't use LLMs now, but they want to use for some like settings where it allows you to like leverage the large internet data, scale data for edge case detection, like a few other things. I don't know what. Yeah, that's all I have information. That's like one of the rooms that was there in AI for the simulator. Like there are multiple houses, and you can have different orientations, I guess. Can I get some water? I'm done with this one. Congratulations. Yeah.
I think they were going to. Congratulations.
Thank you. Yeah, congrats on that. Thank you.
Congratulations.
Thank you.
So if you want, I can share the link, the Zoom link, set it join, and you put them on the screen. And we have a
Oh yeah, yeah.
and you're on Slack, right?
Yes.
Okay.
So I can.
I know.
Look at the password.
Yeah.
So I just joined this.
Yeah, you should be able to run.
Okay.
It's just set to. Or you want to Zoom at the same time?
Yeah, I think so. I think it works. I've done this before.
Yeah.
You can join two Zooms.
Siddharth, sorry, could you put the audio on? Sorry.
Alfred Regalia, so I will put him.
Is it audible now?
Even though it's not official,
Is it audible?
I will. Oh, enhance it.
Yeah, I think it's audible.
Can you hear us? Yes.
Okay.
I will.
Thank you.
This is like European defenses.
Yeah.
They actually have. No,
Comment.
it's a third. I think you get to
Yeah, I
use,
understand.
you defend. I didn't defend, I defended.
Negative.
You have to do the whole.
On the shoulders.
Yeah.
Oh, take a. He gets over in 2 weeks. You have to get it.
Yeah.
I'll click this photo point. Can you move it up? There we go. I'll take another one. Yeah.
Successful defense.
Thank you.
Nice job, very nice job.
I also needed to talk about.
I mean, I basically, you want to
Yeah, I think,